Temos investições muito bem mit internen Teilen. Das ist hier mit weißen Sport. Aber es ist nur auch mit ihm. So,
Yes, ist schon das Frühjahr, aber es weiter mit so zur Fluss. Ja, das ist ja schon. Das sind ja auch einfach Dinge.
Ja, das ist ja,
Is it better?
Das H-Power uns. Modelle H-Stellen, Scheduler H-Stellen. Also wirklich mit der Computation.
Okay, let's get started. Good afternoon, everyone. Welcome to lecture 13 of Fundamentals of Computer Architecture. Today, we're going to discuss about flash memory and solid-state drives, which is another very, very interesting, exciting topic in computer architecture. I had actually kind of difficult time to understand, to decide what to cover. I had like around, I don't know, 700 slides, but definitely I'm not going to cover the whole. So let's see until which part we're going to get, but we're going to learn a lot about SSD architecture, modern SSD architecture, as well as flash memory, how flash memory works. And I'm going to also show you some of our past analysis on flash memory characterization, like flash memory reliability and security. Okay, but before we start talking about flash memory, I would like to, just as a side, I want to talk about emerging memory technologies a bit. Why is that? Because flash memory actually was a kind of doubtful emerging memory technologies, at least for 2 decades. So people were not so optimistic about flash memory, and there were a lot of people that they were working on flash memory to make it possible. And because of all the effort that people made, now we can see the wide adoption of flash memory in our computer system today. And we cannot really imagine today's application without having flash memory. Like the fact that we have smartphone in our pocket is one of the very good examples. That's why flash memory actually made that impact. So we discussed a lot last week about memory robustness, and we basically we talk about limits of charge memory, and flash memory is also considered and categorized as charge memory because it also, you're going to see that it has a floating gate charge, which in the end you're going to store some charge in the floating gate. But essentially, the problem of charge memory is that reliable sensing becomes difficult as charge storage unit size reduces. And essentially, we can have two different solutions. One is that we can come up with new memory architectures to overcome memory shortcomings with using, for example, memory-centric system design, novel memory architectures, interfaces, functions, also better weights management. As we already discussed some of these techniques actually through this course. There are a lot of key issues to tackle, for example, how to enable reliability at low cost, how to reduce energy, reduce latency, and so on and so forth. And we have also worked a lot on this topic. Here are some examples, some of the papers that we have published. And but on the other hand, there is also another solution that basically we can use emerging memory technology. So there are other memory, emerging resistive memory technologies that they seem more scalable than DRAM, and they are also non-volatile. So one of a good example of that is actually phase change memory, that essentially data is stored by changing the phase of material, and data read by detecting the material's resistance. I'm not going into detail of that, unfortunately, for the interest of time. But essentially, in ITRS 2009, they expected to scale to 9 nanometer, and it's also, we have prototype of this memory at 20 nanometer in IBM 2008, and essentially it's expected to be denser than DRAM because it can store multiple bits per cell. That's also the criteria that flash memory has, that you can store multiple bits per cell, but with a different essentially technique. However, emerging technologies have many shortcomings, and that's why actually we and also many other people, they have worked a lot on this topic to make them possible. This is one, for example, industry solution for 3D X-Point as an emerging memory technologies, which is 3D X-Point is actually very similar also to PCM. So these kind of DIMMs, you can actually, you could buy it. I'm not sure if they are still available, but in the past you could buy it and put them on your machine as a normal DIMM. But the fact that these DIMMs are non-volatile, so you can use them for persistent memory, for example. Professor Mutlu and with his also co-authors, they work on this topic a lot. This is one of the very, very first paper that published in 2009, architecting phase change memory as a scalable DRAM alternative, essentially. So basically, people wanted to see where we can put or place these kind of emerging memory technologies in this grand scheme of things. And this is also another writing for that work, which you can also check if you're interested. But essentially, there are different kind of memories that people came up. This is also not complete comprehensive list. There are many also other emerging memory technologies, but PCM is essentially you inject current to change material phase, and then resistance determined by the phase of that material. STT-MRAM is another memory that you inject current to change magnet polarity, and resistance determined by the polarity of that magnet. And also there are other memory like memory store, RRAM, ReRAM, that you inject current to change atomic structure, and then resistance determined by atom distance. If you want to learn more, I would suggest that you check this very recent lecture that we had in computer architecture last semester, that we basically went into more detail of such architectures. But now I'd like to basically get to modern storage, solid-state systems, solid-state drives, which essentially they use flash memory as one of the main basically memory units. And as I said, flash memory was actually one of the emerging memory technologies in 1990s, 1980s. But starting from 2000 or so, they actually started to, make flash memory more available and make it more possible, such that we can use them for our computer architecture. So in this modern solid-state drives in Safari, we are actually working a lot on this topic. We have basically, this is one of the very exciting work that we had in FAST 2018 that we developed a simulator for such a for modern solid-state drive. Now, actually, we are working on extending this simulator. So we are also kind of recruiting, excited people to work on it and make it more useful for today's systems. But essentially, we have worked a lot on improving a storage system as well as also using a storage to do computation. For example, we show that using a storage, you can implement some filtering technique. You can do essentially bulk bitwise operations. Also, you can basically do metagenomics applications. And recently, Mayank also published cipher match that he accelerated homomorphic encryption in using flash processing. So essentially, this topic is actually very, very active in our group. So if you're interested in this lecture, you can actually just approach us, similar to other topics that we have discussed during this semester. But I will start with the overview of SSD organization, that a modern SSD is a complicated system that consists of multiple cores, hardware controllers, DRAM, and NAND flash memory packages. So essentially, your SSD is quite complicated system. Here you can see the NAND flash packages, 4 of them. There are also 4 on the other side of this board. And then you have this Samsung, basically, which is your storage controller, and also some DRAM that you have. Here is LPDDR DRAM. So inside the SSD controller, we're going to see more. Essentially, you have several cores. You have some hardware flash controllers, and these flash controllers are doing essentially a lot of controlling logic that we need to do in order to communicate to flash memory. And as you're gonna actually see a lot compared to memory controllers for DRAM that we actually argued a lot during this course, that we need to make them more intelligent. And unfortunately, current memory controllers are not that intelligent, and they are not doing much, basically, except they are doing that requires signaling to connect to the DRAM. But flash memory controllers, they are quite intelligent. So they are doing actually many stuff, and you're going to see today how we can make that flash memory, which is quite error prone, possible, and you can just reliably access your disk or your SSD and get your data. So you're going to see how much they are doing in order to make it possible, which I think is going to be is a very good example that how much we can get, how much performance how much reliability and performance we can get if we make our controllers more intelligent, as we did also for flash memory. Okay, so essentially in our storage controller, we have a host interface layer and another important layer, flash translation layer, which we call it FDA. And also there are flash controllers. So I will start going over these components at a very high level now, using some example here. We also have DRAM. And in this DRAM, essentially, we have the queue for host request, write buffer, logical to physical mapping. This is something quite key that we're going to see later. And also metadata that we essentially the controller and the scheduler use these metadata in order to make more intelligent decisions. So let's go over these components very quickly, by considering that we want to handle a write operation. So your system sends a write request to the SSD. So the communication with the host operating system actually happens through the certain interface, can be SATA or, for example, NVMe. In the past, we had this SATA, which I think you know, like you were connecting your hard disk drive. With SSD also in the beginning, the interface was actually mostly SATA. But then people realized that SATA does not provide enough bandwidth, that SSD can provide much more bandwidth. So then they developed this NVMe basically protocol that you can access your SSD with higher throughput. But still, and now we have still SATA and NVMe when we are using SSD. So, and also a host IO request, which is coming from the operating system, or can be actually also coming exactly through the process. So with NVMe, actually, we don't have time to go into detail of that, but one of the important thing about NVMe is that each process or each application has a certain queue in the SSD, which without OS intervention, actually that process can access the SSD and write to and read from that queue. So this is one of the important why we are improving the throughput by removing the OS intervention in between. So a host IO request includes several attributes. For example, request direction, whether or not it's read or write, offset, which is a start sector address. This sector terminology is actually coming from hard disk drive, but it's still we are using it for SSD as well for compatibility reason. And also the size of request, which is the number of sectors that we are reading, and as well as basically, and also this request is usually typically aligned by 4 kilobytes, and that's the page size that we usually have in our IO system. So after that, after passing the HIL, which is host interface layer, a write request needs to get to the FTL. And for FTL, basically, we first have this data cache management, and you can essentially buffer the data that you want to write into this write buffer. So that gives you, basically, it's essential to reduce the write latency. You're going to see that writes are actually very, very slow in NAND flash memory. So we have this write buffer such that we write to that buffer and then quickly send acknowledgement to the host, such that the host can continue. And there are some ways, which I'm going to say very soon, that in order to make sure that that write is not going to be, because when you write to the SSD, you're considering that SSD is non-volatile memory, right? So you cannot write to the DRAM and say that, okay, I'm good, right? So essentially modern SSDs, they have some capacitors, and those capacitors provide enough charge. When we have this power cut, those capacitors provide enough charge for de-staging process. There might be some dirty, let's say, data in that DRAM buffer. And when you have this power cut, essentially those capacitors provide charge for that SSD, essentially to write back the dirty data in that DRAM to the flash memory. The power cut, electricity power.
Yes, it's saved in the DRAM, large capacitors, so it leak quickly.
No. Your data is saved in the DRAM, but they are not saved in the flash memory. So from the, sorry? Exactly. So flash memory is non-volatile, but DRAM is volatile. So they make that DRAM actually kind of non-volatile vision by adding some capacitors.
Ah, okay.
Right?
How is that saved for?
So the thing is that that's actually safe, but the problem is that you cannot make that DRAM large much, you know, because if you do want to do that, you need to add a lot of capacitors.
It's not as long as no SATA, though, or non-volatile.
So DRAM is actually volatile.
Yeah, but then it's with the large capacitors.
No, those capacitors provide charge to do de-staging to the flash. So you need some electricity power to write back from DRAM to flash.
Okay, so that can be done during power cut.
Exactly.
Okay.
Yeah. So yeah, essentially that's very important to reduce write latency, and also it enables flexible IO scheduling. It's because basically write latency and read latency are so heterogeneous. By adding this write buffer, you can have more different kind of latency, more balanced latency, and then you can have more flexible IO scheduling. Unfortunately, we don't have time to go into scheduling techniques for SSD, and helpful for improving lifetime. Essentially, you're going to see that flash memory, we have these program erase cycles. Whenever you program to flash memory, you are causing wear out. You know, you're aging your flash memory essentially, and each flash memory cannot tolerate more than a certain number of program erase cycles. So as much as you can write to this write buffer and filter your writes without going to the flash memory, that's a good thing, right? However, that needs actually some locality. So you write to write buffer, and you are hoping that the next write, which is going to be to the same physical location, which is like not physical, to the same logical address, essentially, which is the update. So you write to the address, and you send another update to that address. So if that's the case, okay, this DRAM can capture your new write or new update, which is very good. You don't need to write to the flash memory, but that's very unlikely, because usually on that level, you don't have that much of locality, because your locality hopefully has been captured through the caches and also through the DRAM. So when you get to the SSD, to the storage, locality is not that much. So as I said, the size is limited to tens of megabytes, because it needs to ensure data integrity even under sudden power off. And most DRAM capacity used for logical to physical mapping, which we're going to see next. So this is the core functionality for out-of-place write. You're going to see that in SSD, in flash memory, we don't do in-place writes. So whenever you want to update a page, you basically write it somewhere else. So that's why we call it out-of-place write. Then you actually need a table to say which logical address is mapped to which physical location. And basically, this is logical to physical mapping that we have. And this needs to maintain this L2P mapping, and that tell you that the logical page address LPA map to which physical page address, which we call it PPA. And mapping granularity is usually 4 kilobytes. So essentially, you need to store 4 bytes for each 4 kilobyte of page. And that brings us to this 0.1% of SSD capacity. So usually, people realize that this DRAM mostly is actually, the size is around 0.1% of SSD capacity. So if your SSD capacity is 1 terabyte, you have kind of 1 gigabyte of DRAM, essentially. And most of it is actually used only for basically logical to physical mapping store. So there are a lot of things that we need to do in order to make sure that this flash memory works, like garbage collection, word labeling, refresh, and so on and so forth. And all these actually, they need this metadata, some sort of metadata. For example, this number of program and erase cycles. So how many program erase cycles we have for each block in the flash memory. So this stuff needs to be stored in this DRAM, and then the process, the control process in the storage controller can use this information in order to make decision. So garbage collection, which is gonna see actually today, is to reclaim free pages. And also, because when you write out of place, at some point you are running out of the number of free pages, right? So then there should be a process, which we call it garbage collection, that try to reclaim free pages by erasing some of the old and invalid pages. So we're gonna learn about garbage collection later. I don't want to go into a lot of detail now. And word labeling is another very important function that essentially we want to make sure that our blocks in flash memories, also pages, they are going to be aged in a balanced way. For example, if your flash memory can tolerate 10 to the, each flash cell can tolerate 10 to the power 4, for example, number of program arrays. So one way is to just write to one cell, you know, and just that cell is going to wear out soon, even though there are many other flash pages and blocks that they are useful. So that's not a very intelligent solution, because at some point you cannot use your storage because there are, you know, scattered on basically faulty pages and blocks in the flash memory. So there is a technique which we call it word labeling that try to make sure that we don't have hot blocks and cold blocks. So hopefully we are going to write and do program arrays evenly across all the blocks. So that's the job for word labeling. And data refresh, which is even though flash memory are considered to be non-volatile, but you're going to see later that we actually need to do refresh at least once a week, for example, or once a month. You know, if you, for example, store some data in your cool disk, the flash memory, and you don't touch it for, let's say, 5 years, and after your graduation, you just connect that flash memory, I mean, good luck, you know, getting your data. You might not actually get your data. At least you might be able to recover if you add some, you know, techniques, some ECC stuff, but that's not easy. Okay, so after going through FTL, then we need to go into the flash control. Remember that we were writing, so we were writing the data to the flash memory. So flash controller actually does signaling, which is very important thing for NAND flash packages. So you need to do some signaling, which is such that you can communicate with this NAND flash package. And with that, you need to have this kind of analog, essentially, support to do to send some pulses, importantly, for NAND flash packages such that they can work. But in addition to that, flash controller, for example, does ECC and randomization. So randomization or randomizer is basically does scrambling data to write. So people realize after some characterization that there are some data patterns that they can exacerbate the errors, the number of errors, and or also the probability of errors that we are getting from flash memory. So those are worst case patterns. So people try to use some key, and using that key, they scramble data just to make sure that hopefully we don't have those worst case scenarios. So that's the process of randomizer. So you basically, your data that you want to write, you randomize it with the key, and then you write to the flash memory. And when you're reading, you need to use that key to de-randomize essentially and get the actual data to the host. And also we need to do these error correcting codes, ECC, in order to detect and correct errors. For example, we can store 72 bits for 1 kilobyte of ECC essentially. For 1 kilobyte of data, you store 72 bits for your ECC. Okay, and then after that, you can issue write operation, which you call it flash commands. You send write commands to the NAND flash package, and then you write your data. So when you want to read it, when you send a read request after passing through HIL, essentially you first SSD checks that if it can service your read request through the write buffer, because it can be also considered as a cache, right? So basically first check the write buffer. If so, the system returns the corresponding request immediately with the data. But another important thing is that a host read request can be involved with several pages. So you might want to read several pages, like 10 pages. And then you might be able to service 2 of your pages through the write buffer, but the rest might not be there. So for the rest, you need to access the flash memory physically. So that's why actually the system, this FTL actually waits, or HIL actually waits until you have all the reads, all the pages that you wanted to read, and then send the response to the host system. So that's a very important thing, because you might be able to service the first 2 reads, the first 2 pages very, very quickly through this write buffer, but other pages, you need to wait for them anyway. So that's not going to also, that helps you to understand how we can do some scheduling technique, because if I have to wait, if I have to wait, for example, anyway, so then maybe storing those kind of pages, in the write buffer is not needed much, that's not going to be helpful for you. Okay, anyway. So after, if we don't find our data through this data cache management, we need to check this logical physical mapping, because the host has the logical address, but we don't know that SSD stores the data where. Remember that we have this out of place, right? So there is no map. Basically, you need to check the table to see where exactly your data or page is stored. So you check that, and then you get the physical location. So once you know that which NAND flash package in which, for example, block and in which page store your data, you basically you send the read command to that NAND flash package, and then you get your data. So once you get, flash controller basically performs ECC decoding, and then de-randomize the raw data, and then send it to the host. The thing is that, especially when your SSD is aged, ECC decoding usually fail. And then you need to retry reading of the page by doing some adjustment. So, and that might be one of the important reasons that once your SSD is aged and you are using, for example, your system for a long time, your disk access is going to be slower. So in the beginning, you're going to have very good performance probably out of your SSD, but after 5 years, 6 years, 10 years, your SSD is going to be quite slow, because every read you need to retry a lot in order to make sure that your ECC can handle the number of errors essentially. But you're going to see what I mean exactly by adjusting a reference voltage. Okay, so what is flash cell? A flash cell basically is a transistor that that each transistor, we have this gate source drain, and then when your gate source voltage is higher than a voltage which call it threshold, then the transistor will act as a switch. I mean, not ideally, but as kind of switch. So it's going to be on. And when your gate source voltage is less than threshold voltage, your transistor is kind of open switch. So, but flash cell, the difference is that we have floating gate, and for 2D flash technology. For 3D, they call it charge trap. Is actually different, but overall they are the same at the high level. So here I'm showing the 2D floating gate. So the floating gate, the important characteristic is that it can hold electrons in a non-volatile manner. So when you want to program a flash cell, you basically apply a high programming voltage to the gate. So now, for example, 20 volt. And this 20 volt essentially absorbs some electrons from the substrate and then trap them in the floating gate. So these electrons are tunneling through this from the substrate through this gate. And then here, because of this floating gate, because of the structure, they are kind of trapped here. So now you have these electrons here. Essentially, your gate has a negative charge. So when you want to turn on your transistor, you need to apply a higher gate source voltage. So because of these electrons that they are trapped here, the threshold voltage of your transistor is going to be higher. So that's the key difference here that makes it basically flash memory to work as. So if you don't program in the nominal way, so this is your threshold voltage. When you program your flash memory by adding this, applying this high voltage, you're going to have a higher threshold voltage. So now you can apply a reference voltage as a gate source. If this reference voltage basically turned on your transistor, then you're going to realize that, okay, I haven't programmed my flash cell. So you can encode it as a arrays. Usually people encode it as 1, for example. And if this reference voltage does not turn on my transistor, then I already programmed it. So that's a reference voltage. And then you can encode this state as 0. And that's the way that you can work with your flash memory. Any question? Okay. So the thing is that when you program, and then when you want to basically write, so when you program, you have 0, for example. And then you want to write 1, there is no way to write 1. You need to erase it. And that's the process of erasing, that you apply the negative programming voltage, like minus 20 volt, in order to basically tunnel back these electrons to the substrate and then get to the nominal threshold voltage that you had. But the problem is that this process is not ideal. So whenever you program and you also erase, you might basically leave, you don't push back all the electrons that you had here. You might actually send more electrons or leave some of them here. So, and that makes some errors. And after doing a lot of these program erase cycles, you essentially accumulate your errors. And that's why flash memory cannot tolerate after some certain number of program erase cycles. Make sense? Okay, great. So one of the cool things about flash cell characteristics is that we can actually have multi-leveling. So a flash cell can store multiple bits. Why is that? Because so you can consider, okay, I have only 2 levels. When I program until the end. When I erase, I basically erase fully. And then you can, encode it as 0 and 1. But you can actually also encode it as 2-bit multi-level cell. So when you are programming, you have some middle step as well. So you can actually in your the distribution of threshold voltage, you can be more accurate and say that, okay, if I complete erase, I will encode it to 1, 1. If I program a bit, I'm going to encode it as 0, 1. If I program a bit more, I will program it, encode it as 0, 0, and so on. So that's, for example, 2-bit multi-level cell. Today, actually, we have flash memory that they are QLC, that they are storing 4 bits at each cell. And that comes at the price of reliability and also performance. But when you care a lot about capacity, that's the way you go, essentially. So retention loss is also another important characteristic of flash cell. So a cell leaks electrons over time. So that's what I said. Even though flash memories are considered as non-volatile memory, but after some time, they're basically a cell leaks electrons over time. So this is, for example, the initial state of your cell. After 1 year, you're gonna get to, this kind of charge. Is it still okay? You don't have error. But maybe after another year, you might get to this. And then now you have retention error. Hopefully your ECC should be able to fix that. But when you have a lot of retention errors, your ECC capability cannot, fix everything for you. And also I said that we have limited lifetime. A cell wears out after a number of PE cycling. And that essentially PE cycling affect your retention loss. So after 1 year, if you have only 1 kp cycles, you still have okay, charge. But after 1 year, if you have like a cell with 10 kp cycles, you essentially might have retention error even after 1 year. So these are very important characteristics of flash memory that you should consider. Question? Yes.
Are there actually flash memories setting formula about this? Like now I have too many PE cycles or something like this that I need to replace it?
No, I don't think that's visible to the user. Yes. Yeah. It's actually at the FT level. People are working on open channel SSD that you can implement FTL at the host actually. And with that, yes, you should be able to, to be aware of everything internally. But from the researchers that I'm going to show actually later, we actually build the infrastructure similar to DRAM vendor, for example, and we were studying a lot of these flash memory characteristics using FPGA infrastructure. But yeah, you need such kind of infrastructure to know about what's happening internally. And in general, flash memory vendors, they are not open, to share, as usual, I guess. Okay, so a NAND string is so each of these is a NAND cell. We have another terminology which we call it NAND string, which you can see is very similar to the NAND gate, that you series several NAND cells together. So multiple, like for example, 128 flash cells are serially connected, and so that's a NAND string for us. And whenever you want to read, for example, write, you might have a target cell, and other cell, they are not your target. So the way that they handle it, they will apply a high voltage, which is VPass, and that VPass is actually high enough to make sure that this transistor or this flash cell is going to be on, whether or not you have programmed it or you're not. Essentially, you want to make sure that only this cell, target cell, would basically specify if I'm going to be connected to the ground or not. So this should be the main, the cell that you're going to decide on it. Other cells should be all act as a switch, which you have the connection to the NAND to the ground. If this cell is on, then you have your full connection, and you will encode it as one. If this cell doesn't, so everything is on, but this one is going to be open switch. So your connection to the ground is not basically happening. And then you can encode it as 0, for example. I'm feeling that people didn't get it.
Yeah, I get it. I just don't see what the benefit of it is.
Okay. I guess we're going to see soon. Yeah. So when you want to read, essentially, so you pre-charge this bit line. So that's the process for reading. You pre-charge this bit line. I'm going to show actually later also. But very quickly, you pre-charge this bit line to high voltage. And then you have a sensing circuitry that you're going to see that if this charge is discharging or not, essentially. So depending on this flash cell, if it is on, when you apply reference voltage, it's going to be, might be on, might be off, right? Depending on that, you might see that my current is discharging or not, right? So you want only this flash cell, your reference, basically your target cell, decide if your current flows or not, right? So that's why other cells, they all should act as a resistor. So how is it possible? People apply VPass, which is high voltage, high enough to make sure that this is going to be on, whether or not we have programmed it or not. Okay. Another important terminology is pages and block. So a large number of cells operate concurrently. So this is very similar also to our 2D array that we have also in DRAM. Essentially, this row, we have a word line. And word lines, several word lines are here, 128 word lines, that they work in parallel through all these bit lines. We call it a block, essentially. So this is my block. And there might be other NAND string that they are also sharing the same bit line, but those are other blocks essentially. And yeah, and that's my page. So when you talk about NAND flash page, you are essentially talking about your word line. If you have a SLC NAND flash memory, which you store 1 bit per cell, then your page, you store 1 page per word line. But when you have MLC, for example, that you are storing 2 bits per cell, then your word line, you are storing, for example, 2 pages, right? Okay, so program arrays, they are unidirectional. You already discussed about it, right? When you program a cell, you need to increase the threshold voltage, and when you are erasing, you need to decrease the cell basically voltage threshold. And the programming page cannot change 0 cells to 1, so that's why we need to do erasing. So we do erase before write property in flash memory. And people do erase at the block level. Like the programming and read is actually happening at the page level. But when we want to erase, actually people do erasing the whole block. Like the whole block, they erase it. And why is that? Because erase is actually quite slow. So they want to have high throughput, at least high bandwidth. So they do erase at the granularity of block, which means that makes in-place write on a page very inefficient. So just to give you a clue, assume that you want to do in-place updates. So in this block, there is a page that I want to update it, right? So I cannot update, I need to erase everything. But there are some other pages here that they are, they are valid, and I shouldn't erase them, right? So one thing you need to do is you need to copy paste everything that is stored here to a buffer, to a DRAM. So you need to read everything, keep everything temporarily in a buffer. And then you can erase this whole block, update that page that you want to update it in that temporary buffer, and then store everything back again. Super inefficient. So that's why people just make this basically they do out of place, right? Whenever I want to update, they make this invalid. So that, okay, this copy that I had for this logical address is invalid. It's not valid anymore. And they just write that logical address somewhere else. And they need to update the logical to physical address mapping. We're gonna see, but that's out of place, right? And the reason that we are doing out of place, right?
Update any value in your storage, you just write it somewhere else.
Exactly. Yeah.
And then that one becomes invalid, you can overwrite it whenever you want.
Exactly. Yeah. Yes.
If now one NAND gate is faulty because of too many read and writes,
yeah,
does the whole page or even the whole block suffer from this?
It depends on your FTL. I mean, and actually we don't know because that part is not fully, disclosed. But essentially, it's very hard if you have some faulty pages and you want to still use that page. You want to use that block. Is it still possible? And I know that they are doing it, but in which granularity they can keep doing that, I don't know, essentially.
Just back to the string from earlier. So the reason why they're one after another is just efficiency, right? Instead of having each individual cell have its own individual ground and such.
Okay, could you repeat, please?
So the image before with the string, the NAND strings, that was.
Yes. Yeah, this is NAND
string. The reason why they're connected all one after another is
yeah.
The efficiency instead of each individual one having potentially its own ground would also be impossible.
Exactly.
More expensive, right?
Exactly.
Okay.
So actually, as a good, interesting alternative, we have also NOR flash. This is NAND flash, but we also NOR flash, which essentially the string is a bit different. You have more connectivity, and that provides you better performance, less latency, but then your density and also the cost is higher. So that's why mostly, I mean, today's SSDs, because they want to, have good capacity for good density, they are using NAND flash memory. But when you care a lot about the performance, you might use NOR flash memory as well. Okay. So this is block, and then several blocks, basically a large number of blocks that they share bit lines. We call it a plane. So this is each of these is an NAND string, and they are actually connected to the same bit line, right? So the whole thing we call it the plane, and so there people add two transistors actually to each NAND string in order to control that which NAND string should be able to connect to the bit line essentially. So this, if for example this NAND string needs to be connected to the bit line, we're gonna turn on SSL and GSL transistors, and other NAND string, these two transistors should be off essentially to make sure that we don't have base interference across.
So like the beginning and the end of each block.
Yes, exactly. And then another level of hierarchy, we have die, which is a die contains multiple planes, 2 to 4, for example. This is an example die from a 21 nanometer 2D NAND. And you can see we have 4 planes. And interestingly is that these planes, actually, they are sharing row and column decoders, which means you can actually do some parallel operation across planes as long as the offset is the same. So if you want to, for example, do the same operation, like the read operation, and the offset in the planes are actually exactly the same, then you can do it in parallel. So that's a multi-plane operation that we have actually. There is a command for NAND flash memory that you can do multi-plane operations. But you need to do a lot to make sure that you can benefit from multi-plane operations because normally it's not easy because of this fact that you need to have the same word line offset.
So the only way you can read 4 blocks at once in parallel is if each block were to be in different plane.
So usually you cannot read 4 blocks at the same time. As actually you don't read block, you read page.
Sorry, yes.
Yeah.
4 pages. The only way you can read more parallel is if they were in 4 planes.
Yes, exactly. If they are in the different planes and they are also at the same offset. Yeah. But actually, there is also another command that we have proposed in our recent paper, actually not very recent, Micro 2022, I mean, if that's recent, Flash Cosmos, that we develop multi-word line sensing. And with that, you can actually activate, you can sense multi-pages intra-block and also multi-pages inter-block. And with that, you can do computation. For example, if you activate 2 pages in one block, you are doing AND operation of these 2 pages. But we don't have time to discuss today about it. Okay, so I'm running late. Anyway, this is threshold voltage distribution that essentially you have a reference voltage that we discussed, and then the nominal threshold voltage that we consider naively that there is only one place, but actually there is a distribution. And when you program also, you have a distribution. And why you have this kind of distribution? Because we have variations across the cells. So there are some cells that they are more easily programmed or erased. And so that's why you have different nominal and also program threshold voltage. It's not fixed because of the process variation. So, and this is another example that, for example, we have when we want to store 3 bits in each NAND flash cell, you need to have, for example, 8 states, and you have MSB, CSB, and LSB, and essentially you can encode these states into different encoding, and this encoding scheme actually can be different whether to what you prefer and what you care more. So there is a limited bits of basically threshold voltage window here compared to SLC, if I show you again. So here you have actually much wider region, but when you go to TLC, these windows are actually much narrower, and that basically makes in order to guarantee that we have sufficient margin between adjacent threshold states is actually very actually challenging, and that's why when you go from SLC to MLC and from MLC to TLC and QLC, your read circuitry is going to be more complicated, and also you're going to have also more errors because it's very difficult to distinguish across these regions. And also when you write, and after some time, you have threshold voltage changes over time, which is a retention error, which I discussed. For example, one reason is actually retention error. And by retention, actually, these are shifting to the left. They can be also shifted to the right as well. We're going to see how later if we have time. But actually, normally retention error is actually shifted to the left. But it's not only shifting, they are also widening. So essentially, you can see that the shape of these actually curves is also different, and at some point they have these overlaps, and these overlaps cause errors essentially for you.
So is it mostly just on the sense amplifier on how many bits you can store in a cell?
On sense amplifier, mostly on the read circuitry. Yeah. Sense amplifier, as far as I can say, does not care much. There is a read circuitry, the read controller that needs to retry the read process with different reference voltage. Actually, we're going to see very soon. Let me get to it. So let's see how. Let me finish this part and then we can take a break. Hopefully, short break this time. So basic programming. We want to program a page. We are considering SLC here just to give you the idea. So I want to program this page. So we need to apply vprogram and other cells, as we discussed, we apply vpass, and these two should be on, right? To connect this bit NAND string to the bit line. So there is another important, interesting feature in NAND flash circuitry that you can actually control bit line, and you can inhibit cells to not be programmed. So, for example, assume that you want to write this pattern 0 1 0 1 0. So you know that when it's already erased, I'm storing 1, right? So I don't need to program, for example, this flash cell essentially. So there is a way to do that by inhibiting these cells. If you apply a VCC to the bit line, you're essentially inhibiting that cell. So this cell is not going to be programmed at all, because by controlling which voltage you are connecting to you're driving to the bit line essentially. In order to fully understand it, you need to know the detail of the circuitry. But this is important. This is just to give you an idea that you are able to control every single cell in the flash memory. So when your page is already erased, this is the distribution, right? Everything is erased. So if you apply vprogram, you want to get to this, right? So there are some inhibited cells that they will stay in the program, in the erased basically state, and other cells, they need to be programmed in the program cells, right? But unfortunately, when you apply vprogram, you get to this kind of curve. So if you apply vprogram at once, there are some cells that they are easy to program, so they quickly get to this high threshold voltage. But there are also some cells that they are hard to program, so you need to wait more and apply more voltage essentially. So in order to fix this problem, people came up with this idea of incremental step pulse programming, ISPP, that essentially instead of applying vprogram at once, they have incrementally increasing the vprogram. So they have a vprogram 0 and they apply. And then after that, there are some cells that they are already programmed. So after one program 0, they check. So these, for example, yeah. So after a program, we verify and we realize, okay, this cell is already programmed enough. And then for the next cycle, they inhibit this cell by adding VCC to the bit line. So this cell does not need programming anymore. And then we will repeat with another program voltage, vprogram 1. And then after some time, we get to this, our beautiful curve that we wanted.
Is this after the storage is aged? Or is it...
No, actually from the very, very beginning. You need to do that.
Just quickly, is it also destructive reads?
No, on that, it's not destructive read. Destructive in the meaning of DRAM that when you're reading, no, it's not that. But when you read, you might have some read disturbance similar to DRAM, and also write disturbance you might have.
So this program 1 is higher than program
Yes,
0?
yes, exactly.
But then wouldn't it be better to just apply this higher voltage to everything?
So that might first of all, you need to, if you apply that high voltage at once, you should also wait enough. And then the problem is that those cells that they are easy to program, they may actually program a lot. That's the issue. Then
when you try to beat them,
yeah,
they one distance.
Exactly. When you are SLC, maybe you don't care, but if you want to really accurately manage this window with, for example, TLC and QLC, you really need to be so accurate.
And just double check, if you were to erase an entire block, that means the entire block is spaced just a load of ones.
Exactly.
Okay.
Exactly. Okay, interesting. So when you want to read, you essentially have you need to apply reference voltage, as we discussed. So in SLC is actually easy. You apply reference voltage here, and you need to charge all bit lines. Basically, they're going to be VCC, and then basically you're going to monitor if the current flow or not. Here, for example, the current doesn't flow, so you know that when I apply reference voltage, this cell acts as an open switch, meaning that I already programmed it. So you will encode it as 0. This one, basically, my current flows, so I will encode it as 1, and that's how it is. There is a circuitry here that understand that the flow, the current flows or not, which I'm kind of ignoring at this moment. And I have it in my backup slide. If you're interested, you can check. But yeah, but at the high level, this is how it works. But when you want to read in a TLC, in MLC, for example, then actually here I'm showing. I mean, MLC, people mistakenly usually think that is actually storing 2 bits, but MLC is saying that multiple or multi-level cell. So TLC is also MLC essentially in the end. But TLC, here I'm showing, we have 8 window. So assume that I want to read basically the CSP, which is the center bit. So we apply, so we have 7 different reference voltage essentially to distinguish across each of these windows essentially, right? So you have many, it's like 7 reference voltage. So when you want to read the CSP based on your encoding, you need to see what are the reference voltage that they are important to you. So those reference voltage that you are observing some toggling, those are the reference voltage that you need to be careful about. Like here, for example, 1 goes to 0. So this reference VREF1 is important for me. Also here, 0 to 1, ref 3 is also important, and ref 5 is also important. When I want to read CSP, for example. Okay, so the way that you do, you apply first reference 5, and then you read, like as if you're reading from SLC, right? When you apply this, basically everything before every voltage threshold below VREF5, you're going to encode it as 1, right? And everything above that, you're going to encode it as 0. So you apply VREF5, and this is basically what you're going to read: 1 1 0 0 1. You're seeing that almost is correct, but this one is not correct, because for this 0 0 0 actually is here. So I had to have a, for example, I had to have a I had to use VREF1 in order to understand that this is programmed. Correct? So essentially, you need to repeat the read procedure by applying other reference voltages that they are important for you. So here, we also need to apply VREF3, and then we read. So we have 1 1 0 0 1. And then we apply also VREF1 and we read. Okay? And then you need to have a technique to logic such that you combine whatever you have read such that you get to the actual data that you have to. So this encoding actually very exciting, because by XORing what you have read, you're going to get to the value that you need.
I don't understand why we're reading from the center bit.
It's just an example.
Oh, okay. But normally you'd be reading all 3 bits.
No, not normally, actually. Actually, normally you read one of them because you want to read, for example, page. So we are storing 3 pages, for example, in a word line, right? So you want to read the center page, for example.
I thought it was always like you had 3 bits of the same string back to back.
Usually it's not
saving 3 different data types on the same line.
Yeah, I mean that can be also the case, but usually people don't do that. People store multiple pages, different pages in a TLC, for example. Yeah. Okay, so this some takeaway. Essentially, we need this XOR logic, and bit encoding actually affects the read latency. So here is a very cool example. With this TLC, I'm showing 2 different encoding, for example. So the above encoding is actually what we had before, but the below is different, right? Is a different encoding. So now you can actually have fun with comparing like the number of reference voltage that I need, for example, to read LSB. So in the above this basically encoding, when I want to read LSB, I need to apply only reference VREF0 and VREF4, because these are the only, the two reference voltage that I'm observing toggling between them. But for this one, when you want to read LSB, you need to apply 4 reference voltage. Clearly, reading LSB if you use this kind of encoding is actually slower, right? But there is a trade-off here. When you want to read MSB, for example, here you need to apply 2 reference voltage, but for this one you need to apply only 1 reference voltage, right? So that shows you essentially that by changing the encoding, you can have different latencies and trade-off. And actually, there is actually kind of active research going on. That, for example, this one we observed that reading MSB is much faster compared to reading LSB. With LSB, I had to apply 4 reference voltages, meaning 4 read process. But for MSB, I only apply 1 read process. And people try, for example, say that, okay, the MSB page can be used as a cache for LSB pages, for example, right? Because MSB pages are faster, or that doesn't need to also be cached. For example, you want to store some pages that they are more latency critical. So you are storing them in MSB pages. Those pages that they are less critical, you are storing them in LSB pages. That's, for example, one of the trade-offs that you can make. But you can also have fun with more trade-off. Okay, let's take a break. Let's have a 5-minute break if possible, and then we will continue afterward. Thank you.
Und wenn du das alles löschen hast, du hast eine oder ein paar, wo es negativ ist, Spanisch, normalerweise du kannst so viel erasen, also das ist schon der Code, sind die noch wieder extra, in normale Zeit, und dann ist immer was That's what I think. I have a question. Yes. You mentioned that some cells degrade faster than others, and you have to, what is it, they send a higher and higher voltage until they get the correct output out, right?
During the write process, you mean?
For
So some
because you mentioned that some of them are hard to, was it write or read? I can't remember.
Yeah, exactly. So there are some. So when you apply a programming voltage, some cells quickly get
quickly get it, and
get charged.
Like keep reading until they finally eventually get it.
Yeah, exactly. Okay.
And then you just check every time. So is it
exactly
a read essentially? Do you ever
exactly. So you write with the programming voltage, and then you immediately read what you have written. And if then you inhibit some cells, and then you basically keep.
I was thinking you could just add some like metadata to like the DRAM about the entire cell array, figuring out which one of them is slower to write than others, and then you could just immediately from the get-go.
Yeah, that could work if those cells are, the number of them are manageable, So you don't know.
I just assume at one point you mentioned metadata. And
That, yeah, exactly. So the problem is that even so, there might be some pages. There might be some pages that only a few of cells are problematic, but the other pages that they might have a lot, many pages, many cells that they are problematic. So in the end, if I want to summarize, like the fact that we have flash memories working today is a magic. Like, I mean, it's not magic. It's because of all the research and effort that people have made. But these you're gonna see actually later today. Flash memory you can actually you know you can consider it as a noisy channel. Like you write in a noisy channel, and when you read, you're reading noisy essentially. And then you need to do a lot to make sure that you can work with that noisy channel.
Yeah. Okay. Yeah. And this is also the same as what you mentioned earlier, is the hot pages.
Yes.
The same thing, right? Okay.
No, hot pages are pages that you might write to them a lot. For some reason your word leveling might not be effective enough, and you might do a lot of writing some blocks. So when you, in the end, when you count the number of program arrays for every block, there might be some blocks that you have, you use them a lot. So you call them as hot blocks. Okay. And those blocks they're gonna wear out quickly, essentially. And there are some cold blocks that they are not, they have time, so you're gonna swap them. Yeah, exactly. And it's easy with flash memory architecture swapping, because you have this logical to physical mapping, right? So you have the possibility. In DRAM, for example, we don't have that easily. So when you are remapping it's not actually, remapping is not an easy way, it's not an easy thing to do in DRAM, for example.
Is it because DRAM just got more precious capacity, like just more precious cells, so you can't afford to just take some other random location, just ignore that one?
No, but even if you realize that, okay, there are some rows in DRAM that they are faulty, for example, and you don't want to use them, so you need to remap to somewhere else, essentially to another row. So I think you can still do that from some of the analysis that we had, but it's not. So the circuitry is not there much. So you're not that flexible when you're doing remapping. You need to be more careful. Okay, let's continue. So there are actually a lot of things that I didn't cover in the first part. For example, there are a lot of advanced commands in NAND flash memory to improve performance that you can check them in my backup slides. And I'm going to also, put some links to other lectures that you can check if you're interested. But I want to also quickly just give you the basic of address mapping and garbage collection. So we discussed about this flash translation layer, that it provides backward compatibility with traditional HDDs. Actually, that's one of the important feature, or let's say task of FDL or SSD firmware, to provide that backward compatibility for you. And that happens by hiding a lot of characteristics of NAND flash memory. So there are many things which they are specific to flash memory, and your system does not need to deal with all of them. So the FTL is actually doing that to make a very nice interface for you. But in addition to that, FTL also does a lot of for making sure that flash memory works well. So some of the important responsibilities, for example, address translation and garbage collection that we're going to see, word leveling that we already discussed a bit, and data refresh and I/O scheduling. Hopefully, we're going to see, I mean, this one for sure, and data refresh also in my future slides. But I will let you check word leveling and I/O scheduling later through my backup slides. So this is let's start with an example. A very simple SSD architecture. We consider we have one plane, single plane, and we have 5 blocks, and in each block we have 4 pages. And this is the way of the whole system, the way that the file system or the I/O block actually looks at your SSD is actually kind of continuous array. So your logical address space, for example, is 16 basically pages. So this is a storage view at the operating system level, a flat block device, and each of them is logical block address. And that's something that people gets a bit confused, because this block is actually consider one page here. So the terminology of page and block is different at the OS yeah, exactly, compared to the SSD. So we have physical block address. So this is the address for physical block address, and also physical page address at the SSD level. Okay, so and you can see that we have kind of over provisioning here, that physical capacity is greater than logical capacity, and that's something that always happen in SSDs. So when you buy, for example, SSD with 1 terabyte, that SSD actually internally has much more than 1 terabyte. To make sure that we can do this out of place update as much as possible. At some point you cannot, and you need to do garbage collection that we're gonna see. Okay, so we receive a request from the host to the logical block address 0, and the size is one sector, and the direction is right with the data. So essentially your plane is completely empty. Your SSD write this A to this block 0, page 0, essentially. So we are assuming here that logical block size equals to physical page size. So basically 4 kilobyte and physical, but usually the thing is that normally in our SSDs, the physical page size is actually 16 kilobyte. But that's something that I kind of ignore now. And you can check my backup slides for fine-grained mapping if you're interested. But this is for simplicity, we consider that these two are the same size essentially. Okay, later on, we receive another write request. Start from logical block address 4, the size is 12, and the direction right, and this is all the data. So you might think that SSD actually starts to write from, because this 4 and here is 4, so nicely I can write, right? And then even this is also 15, this is also 15, so all good. But the thing is that SSD writes like this. So starts from continuing from block 0. And why is that? Is actually from the reliability reason. Once you have a block open to write, which we call it open block, you want to write to that block as much as possible, as fast as possible. Because keeping a block open actually causes reliability issues for the data that have been stored already. So that's why block 0 now is open. So I will continue writing B, C, D here. And when block 0 is full, then I go to the next block and open block 1 and then write to it also. So that's the way we write. This is talking about this active lock problem that I already talked about. So now you can see that later on when I receive a read operation for logical block address 4, basically we don't know from where I should read, because physical page address now is different. It's not 4. So that's why we need to have this address mapping, logical page address to physical page address. That tells us that basically logical block address 4 maps to physical page address 1. And by getting this information, you can access your flash memory and get your data. Okay, sounds good. So later on, you receive another write, which is actually kind of considered as update, because you are writing another value to the logical block address that you have written in the past. So now you have update. The problem, what we are doing here is that we do out of place update. So the open block now is block 3. So we just write A prime there. And then we need to make this one invalid. So that one is not. And also we update this location that this is the the new location for this logical page address. So we receive another update, we update, invalid update. And at some point we are running out of free pages. Okay, so now we get to this garbage collection to reclaim free pages by erasing invalid pages. So now you can see that we have, for example, a lot of invalid pages, right? So we can try to erase them to reclaim free pages. So erase unit is block. So if a victim block, the block that we want to erase, has valid pages like this. So here, for example, if block 3 is your victim block, 3 of them are invalid, but you still have a valid page, right? So essentially, you need to copy all the valid pages need to be copied to other free pages, and that comes with the performance overhead, because you need to read all these valid pages, and there might be a lot, and then you need to write them somewhere else, and that causes lifetime overhead as well. So usually, there are a lot of policy for doing a garbage collection. Simple one is greedy. that you essentially erase the block with the largest number of invalid pages. So you want to make sure that we have less number of valid pages, because the problem is copying valid pages. So then we need to maintain number of invalid or valid pages for each block. How we are doing that? We add a status table to our FDL. And for each block address, physical block address, we are giving the status. So here, for example, for block 0, we know that the first one is invalid and the rest is valid. And for example, for block 4, we have valid and 3 free. And for block 3, we have valid and 3 invalid. So now I want to invoke garbage collection. Basically, I will select victim block, the one that has the highest number of invalid pages. So this one I will select it. I need to essentially write, basically read the valid page, which is read the address 12, and then program it somewhere else to make this one invalid. And then I need to also update this status table and also update the mapping. So we also need to know that this physical page address 12 initially was mapped to logical page address 15. And now I need to change this to 17. So normally you cannot do that because this table actually only stores this way from logical page address to physical page address. You cannot get the logical page address associated with to physical page address. How we do it? Essentially, we in each page we have some area which we call it out of band area, that we store that this page belongs to which logical page address. So we are using some out of band area in each flash page to basically store that the logical page address for that. And we are using that in order to understand that this is logical page address 50. Yeah. So you update, and then now block 3 is all essentially invalid, so you can erase it. And now physical block address 3 is all free. So you update the status. And you can use this block 3 for future writes. But just to make sure, just to let you know, this erase operation, you are doing it, you don't do it immediately. Because once you erase a block 3, you make block 3 active. You make block 3 ready to be written. And you want to do it when you really need to do it. So usually we invoke garbage collection actually a bit ahead of time. I don't wait until I don't have any free pages or I have only a few pages, and then I start doing garbage collection. So SSD starts doing this garbage collection, for example, when SSD is not that much active, invoke it to reclaim some free pages. So there are some blocks that they all have invalid pages and I can erase them, but I don't do it immediately. I will wait until I have to do it,
So just before the writer,
for example, yeah.
Requested, but then how would it be done ahead of time? Would the CPU orchestrate some sort of command?
No, the thing is that when you, so when you, well, no, we don't have that kind of information, but when you write, you usually write to the DRAM, right?
Oh, so during that write to DRAM,
you have that information, yeah. Okay, so garbage collection actually causes a lot of performance issue. And because of this, for example, copy, a block, for example, can contain 576 pages. If you, for example, assume that only 5% of pages in that victim block are valid, basically you need to copy 5% of this number of pages somewhere else. So you need to read and program, and the number of pages that you need to copy is around 28. And garbage collection latency is going to be at least 28 times reading and programming, and also erasing, essentially. And this actually a lot, like 27 millisecond, which is orders of magnitude larger latency than read and programming. So that's why actually garbage collection is so expensive. And if FDL, for example, performs garbage collection in an atomic manner, it delays user requests for a significantly long time. So previously in the past, it was the case. When you were profiling your SSD, the performance was good, but at some point garbage collection starts and you were seeing actually significant drop in your performance because of garbage collection. So there are some mitigation techniques that people came up, like trim is a command that people basically propose it at the software layer, at the OS, that we can inform FTL of deletion or deallocation of a logical block. So at your system, when you delete a file, normally you don't inform SSD or hard disk that, oh, I delete this file. You're going to just delete from the page mapping that you have at the OS, right? But with trim command, people tell you that, okay, when you deallocate or when you delete something, you can inform SSD that this page or these pages are not valid anymore. So then SSD does not need to basically copy them, through the garbage collection. So with trim command, you can inform FTL that to skip copy of obsolete or invalid data, essentially.
So you just essentially switch the bits to invalid.
Yeah, exactly. Yeah, but that command was not there. So because when SSD started to be used more and more, people have been using the IO system or IO block that has been proposed for hard disk drive. But people started to look into, okay, how much I can improve it, like to make it more specific to SSD. And that trim command was one of the things that is already added to Linux, for example. Linux kernel, you can do it. You can also do garbage collection at background. So the challenge is that how to accurately predict SSD idle time. People have worked on it. There are heuristic techniques. There are also machine learning techniques that to understand that when SSD is idle to schedule garbage collection request. You can also do progressive GC that you divide garbage collection process into subtasks. For example, if you want to copy 28 pages, you copy one page and then you service one user request. And then do it multiple times. So you don't, for example, do, okay, I'm copying 28 pages. I'm not going to do anything else. And when I'm done, I'm going to service some other resources request. Basically, you're going to do it progressive, essentially, And that is very effective at decreasing the tail latency of your request. Question? Yes?
Where is the mapping table and how is it actually stored?
So mapping tables is stored in the DRAM. And that internal DRAM of the SSD.
And how do I
not
use it like a week after?
So actually, yeah. So the actual mapping table is stored in the flash memory. But when you want to use your SSD, that mapping table should be loaded to your DRAM, to that internal DRAM that you have inside the SSD. Enterprise SSDs, that DRAM is large enough to house the whole mapping table because you want to be fast. But low-cost SSDs, the mapping table is not large enough. The DRAM is not large enough, so you cannot house the whole mapping table. So people came up with caching technique. Like DFTL is one of the cool technique proposed in ASPLOS 2009, if I'm not mistaken, that they try to cache mapping table, essentially. So you can also think of prefetching, caching, like all these things have been, you can also revisit there as well. Okay, very good question. So I covered most of it. I didn't cover IO scheduling and flash memory array parallelism. For that, you can check previous lectures in the past and also my backup slides. But I want to also go into error characterization in flash memory mitigation and recovery. This part is 3 hours by itself. But clearly we are not going to do that, but at least I will give you some idea about it. Question? Are you excited? This is a cool topic at least, right? Okay, so this survey, error characterization, mitigation, and recovery in flash memory-based solid-state drives is actually summarize many of these techniques, all this characterization that Professor Mutlu's group, they have, and also other papers that they have done to understand basically flash memories, reliability, and basically characterization, and also provide some mitigation and recovery techniques. So fortunately, I don't need to go into background. You all know all these stuff. Floating gates, how we write. Okay, good. This is a slide that I already talked about it, NAND and NOR. You can see that in NOR flash, actually, we have much more connection to the bit line and is actually faster. But the problem is its density, which is lower compared to the NAND flash memory. Okay. Yeah, this is also the problem of retention loss that we already discussed. and we're going to have errors after some time. This paper actually talks about how we store multiple pages in MLC NAND flash memory. So if you want to understand, how they map different pages to a MLC architecture, you can check this paper actually. Okay. So many of the work that I'm going to discuss, they are considering planar NAND flash memory, which is 2D. So I want to give you just a very quick story that essentially in 2D flash memory, so the vendors, they wanted to, improve the capacity. So they made the flash cell smaller and smaller, and you can guess it. So when you make it smaller and smaller, like DRAM also, you have much more reliability issues. So, and actually they reached to the point that they were kind of struggling, how they can, provide better capacity, why they don't, but not at the price of even worse reliability, essentially. So then 3D NAND flash memory technology actually comes to play, and that gives some freedom to the, or let's say breathing room to the vendors, and they could provide some capacity through the, the 3D architecture, and they were using larger cells. So by using larger cells, they could provide better reliability, and they provide the capacity vertical, through the 3D architecture. So at that time, this 3D NAND flash memory was not well studied, let's say 2016, 17 or so. But now there are also some works that they also discuss about 3D NAND flash memory reliability and so on and so forth. But the thing is that back then, people haven't observed much of reliability issue when they use 3D NAND flash memory because cells were larger. But again, you can guess it. As we wanted to have more density, then they have to, even for 3D NAND flash memory, they also had to make it smaller and smaller. And now we have even different, and it can be actually severe in some cases, issues that we have. So this is structure of 3D NAND flash memory. I'm not going to into detail of it because the part that I'm going to talk about it today is not actually related to 3D flash memory. But you can check the backup slides if you're interested. Okay, so we discussed about limits of charge memory, and essentially the problem is that MLC NAND flash memory reliability and endurance is a key challenge for satisfying future storage system requirements. And our goals at the time was to build reliable error models for NAND flash memory by experimental characterization and develop efficient techniques to improve reliability and endurance. So by having so flash memory have ECC, and ECC can correct some of the errors, but ECC are usually good for things that you don't know. Like there are some errors that you don't know the source of them, right? So once you have an error and you can understand why such errors are happening, you should be able also to design some techniques, some architectural techniques to mitigate those errors, essentially. And then that reduces how much you rely on ECC, essentially. So you could get the same reliability actually by using much smaller ECC, or using the same ECC, but then you get much longer time, the higher endurance and lifetime for your flash memory. So that's why these kind of works are quite important. So this lecture is going to be actually a flash summary of our recent results in the past 10 years. And these are some papers that I'm going to, not all of them, but yeah. Okay, so this kind of evolution of NAND flash memory from 1998 to 2010 and so, that essentially you can see that flash memory is widening its range of applications and portable consumer devices, laptop PCs, and enterprise servers, essentially. So the problem we have with flash is reliability and endurance. This is the endurance results for at the time. That for SLC you have kind of around 100,000 endurance, the number of programmable cycles. For MLC is lower, and for TLC is much lower. So the PE cycles provided is few thousand, specifically for TLC. However, the PE cycle required based on this standard is actually 10 times per day for 5 years, which means that you need somehow more than 50K PE cycles. So there is quite a big mismatch between what you have and what you need. So the question is that how we can hopefully bridge the gap by using more intelligent technique to provide reliability. So endurance of flash memory decreasing with the scaling and multi-level cells, which you can also guess it. Like when you use MLC, you have much less reliable. And also when you're scaling it, your cells are smaller. This is also very similar to DRAM, the issues that we have. And then in order to have reasonable PE cycle, you need to add stronger ECC. So you need to increase the complexity, the error correction capability in order to basically tolerate and provide some reasonable endurance. Okay, this is what I talk about it. That NAND is kind of noisy channel that you write it and read noisy. So you from this noisy, you have this memory signal processing. And with that memory signal processing, hopefully you can get some lower row bit error rate. And then you can have a much better error correction code, or let's say less costly error correction code, such that you get to the uncorrectable bit error. So this is the standard, which we call it uncorrectable bit error rate. It should be less than 10 to the power minus 15. So the goal for ECC is that we need to get to this rate. So when your uncorrectable bit error rate is higher than that, that means that this is not a medium that you can use it as a storage, for example. So that's the standard, essentially. Okay, so the goal is to build reliable error models for NAND flash memory and design efficient reliability mechanisms based on them. Okay, I can kind of skip these things. So these are different papers that we have published to understand and characterization, and also where to be apply technique to when we want erase block, when we are programming page, neighbor page program read cell-to-cell interference and retention error. I think I already discussed about this. Okay, so this survey is actually full of information. I would recommend everyone that if you're interested in understanding all this stuff, check this one. It's very actually informative survey. But let me show some of the results. So this is the infrastructure that we had at the time. You can see another Vertex 5 FPGA, and we had this NAND controller. There were some NAND company that they were helping us to build this technology, and basically to have this kind of NAND controller, because having NAND controller is also a big challenge, and that's why they help us. So there are 4 types of error that can cause. So one is caused by common flash operation, which is read errors, erase errors, and program errors. And another one is caused by flash cell losing charge over time, which we call it retention errors. Okay. Essentially, in all the pipeline of NAND flash memory, you can have errors. So when you erase block, you have erase errors. When you have program, you have program errors. When you also have retention errors, you might have read errors. You have retention errors. Basically, you have error everywhere. And that's why actually when flash memories are quite error prone. Okay, so let me show some results. So here in this plot, you can see that essentially row bit error rate increases exponentially with PE cycles. So when you have higher PE cycles, row bit error rate is much higher. I should also say that this row bit error rate before ECC. So hopefully your ECC should be able to reduce this, basically make this bit error rate in less than 10 to the power minus 15. So when I say that row bit error rate, basically essentially the error rate that you observe before applying ECC, essentially. Okay, and retention errors are dominant. So more than 99% for 1 year retention time, and retention errors increase with retention time requirement, essentially. So essentially, electron loss from the floating gate causes retention errors, as you can imagine. But the interesting thing is that cells that they are storing more charge. Actually, they are more. They have more retention errors. So in this plot, we actually show different patterns, like how much error we got, for example, from going from 0, 0 state to 0, 1, for example. This one. So you can see that this one is a big chunk, and from 0, 1 to 1, 0 is also another big chunk. But other patterns also we have observed some of them, but they were not that probable, as you can imagine. Okay, So you can check this paper for seeing all these error patterns in MLC NAND flash memory. But now I want to see how we can do some management based on this understanding. So solution to retention errors is we can refresh periodically, as we also do in DRAM. Hopefully, we don't need to do it as frequently as we do in DRAM. But still, if you want to avoid retention errors, you can refresh. So you can change the period of which you are refreshing based on the PE cycle wear out. When your cell or block is still young, you don't have that many PE cycle, you can actually do refresh less frequently. But when your device is quite aged, like for example, you have 10,000 PE cycle, then you might want to do refresh more frequently, just to make sure that your device is working correctly. And you can actually use a combination of in-place and remapping based refresh. So when you want to do refresh, you can just write to somewhere else. So before losing your data, you read and you write to somewhere some other pages, similarly to out of place update, right? Just write to somewhere. So that's a refresh. But you can also do in-place refresh, which is interesting, and I'm going to show it. But that's is mostly possible actually in SLC devices. In MLC, it's very hard to do in-place update without losing reliability because of adjacent rows or pages. So we had some key observation here. Retention errors are the dominant source of errors in flash memory, and the that limits flash time as they increase over time. Okay. Retention errors can be corrected by refreshing each flash page periodically. And the key idea is periodically read each flash page, correct its errors using weak ECC. So hopefully you don't need that much strong ECC because you don't wait until you have a lot of errors and then you really need a strong ECC to correct things. So you write, and after some time you read, and hopefully by that time that you are reading, the number of errors is not that much. So you can fix them with weaker ECC. And then you either remap it to a new physical page or reprogram it in place. So, and basically you should be careful to do it before the page accumulates more errors than ECC correctable capability. Okay. So there are two key questions: how to refresh, which I already discussed. You can do remap or reprogram, or you can do hybrid. And also when to refresh, you can have fixed period, or you can be adaptive for example, to the retention, to the number of PE cycles, for example. So in this paper, we realized that essentially hybrid and adapt the period is gonna actually lead to a better solution. So how we do in-place reprogramming of flash cells? So after some time, basically retention errors are caused by cell voltage shifting to the left. So you're gonna have this kind of, distribution. So you can actually do ISPP to move cells voltage to the right, essentially. So you do that ISPP a bit, and you need to be careful. But essentially, you do ISPP, and then you read, and then you check ECC, and hopefully you should be able to fix errors. And then you already, after some time, you can see that, okay, I already fixed the problem. I refresh in place. So the problem, I'm saying that this one is actually less effective, or at least it's not easy to do, because when you do in-place update, so when you're so later on, you're going to see program interference, essentially. So when you're programming, you're actually doing some interference to neighboring pages. So when you're doing in-place updates, actually you are adding some, accumulate some errors to the neighboring pages that you have in that flash memory, in that block. So when you have SLC, this might not be a big problem because you have room, to error. But when you are using TLC, for example, or QLC, in-place update is not easily actually doable. Any question? Yeah, as I said, the cons is actually increases the occurrence of program errors, which you might not be able to tolerate it if you have TLC or QLC, not flash memory. So with this, we observed that, for example, having a remapping based, having hybrid FCR and adaptive FCR, which is the best technique, we can actually provide a much higher lifetime. So yeah, so improve lifetime base compared to the baseline. Okay, and the energy overhead. So using adaptive rate refresh still is less than 1.8% energy increase until daily refresh is triggered. So as long as you are refreshing less than once per day, your energy overhead is less than 1.8%. But at some point, your block is so aged, and you need to do it more frequently, like every day or even every hour, and with that, then your energy overhead is going to be much higher. Yes.
So with remapping based refresh, isn't that like a devil's circle because it degrades it even more?
Indeed. Okay. There is a paper that talks about it, but I actually have it in these slides, but I'm not going to reach to that point. But that's a very good point. Yes. Okay. Check this paper again. It's a very interesting paper to read. Okay. How much time we have? Okay. I can still also. Any question? Okay. So now let's look into threshold voltage and program interference analysis. So there are some key questions that here we want to ask, like how does threshold voltage distribution of different program state change over flash lifetime? And can we model it accurately and predict the VTH change? So if you can model, you have a model that tells you that, okay, which, so my threshold voltage is going to be what amount, after some time, after the number of PE cycles. So then you can use that model in order to get to the optimal reference voltage that you need to access your flash memory. Okay, so we work a lot on this, and then use some of these. You can see the distribution across different number of PE cycles. And then let me see. Yeah, so essentially we came up with a model. And that model can model with 95% accuracy as a Gaussian distribution with additive and white noise. Later on, also, we improved that model by adding a student's T model, which I have a slide, but I'm not sure if I'm going to get to that. I think I can get to it actually here. So this is a, so there are some cases that you have problem, like, so these are the actual, the distribution that you have. So your Gaussian model is going to tell you this, dot curve. But there are some parts, that, for example, is happening here. So you should be able to somehow basically predict them. And with that, we actually use a student's T-based model in order to, to model the whole plot, the whole distribution. And actually, student's T-based model provides the results similar to Laplace model, but is actually much faster. So it's easier to do it at runtime, essentially. Yeah. With normal Laplace, you are getting the same average, more or less. This is the average of basically the error that you are getting. And essentially, with you can get to this, use this student's T to get have a good trade-off between Gaussian and normal Laplace. Okay. So now you can use actually this kind of model in order to design technique for better reliability. So when a cell is being programmed, voltage level of neighboring cell changes, and that's, we call it as a program interference error, and that can cause the distribution of threshold voltage to go to the right. Okay, normally I talk about retention errors, but this can actually increase. So this is just a reminder how we do programming. So here is my victim cell, and all over it we have some writes, even in the same word line and also other neighboring word lines, and all these, they're going to have some delta voltage changes, and everything can affect the threshold voltage of the victim cell. Actually, people realize that the cells at the bottom, actually the lower, they don't affect much. So it's mostly actually the top and also neighboring. And yeah, and so this is the traditional model for victim cell threshold voltage change. So the problem with this model is that this is not accurate enough. And also there are some values that you cannot easily calculate, like coupling capacitors is not easily calculatable. So our goal was to develop a new, more accurate and easier to implement model for program interference. And the idea is to empirically characterize and model the effect of neighbor cell threshold changes to the VTH of the victim cell. So this is the model that we wanted to learn. And essentially, these are the things that you can calculate. So these are different, like the change of the voltage in the neighboring cells, and also some parameters that you can also train them using your analysis or characterization. Okay, so here is our analysis that our victim cell, we observe that immediately above cell interference is dominant. So this cell is going to be the most important one to affect the threshold voltage of the victim cell. And then immediately diagonal neighbor is the second dominant. But also far neighbor cell interference exists also. So these all far neighbor also, they affect the victim cell threshold voltage. So as a result of all of these interference, we observe that, for example, the threshold voltage of this cell has been changed by, for example, 2%, for example. Okay. So we actually designed this model, and then the accuracy of this model is quite reasonable, as you can see from this plot. Okay. Let me see. Any question? Let me also quickly go into key idea of the second one, and then I think we are done. I was not planning to actually go over others, so I think I got to the point that I wanted. So what can we do with the model? The goal is to mitigate the effect of program interference caused by voltage shift. So after some shift, essentially, when you have some overlap, there is an optimal reference voltage. When you apply that, hopefully you have less number of errors. So the idea is that we should have less number of errors, such that ECC should hopefully is able to correct the errors. So when we have that kind of a state, actually having the reference voltage is okay, is easy. But the problem is that we might have this kind of variation, that our reference voltage is actually here, and you can see that we have different overlap. So now actually I need to actually adjust the reference voltage. And so the reference voltage that is here is actually going to be better, the optimal one. So the goal is to learn, like understand that where I'm standing, and then adjust the threshold voltage, the reference voltage such that you can get to the optimal number of errors, essentially. So you need to predict this threshold voltage shift, essentially. Okay. So we have this threshold shift learning, which is done every 1 kp cycles. You program sample cells with known data pattern and test, and then program aggressor neighbor cells and test victim threshold voltage after interference, and you characterize the mean shift in threshold voltage for which is, we call it program interference noise. And then once you have it, then you design optimum reference voltage prediction. So we default reference voltage plus predicted mean VTH shift by model. So the model tells you that, okay, how much you need to add to your reference voltage in order to correct. And with that, you can actually improve performance. This is the plot that I wanted to actually talk about, and then we are done. So essentially, you can see that having the same ECC support using 32K bit BCH code, you can actually increase the lifetime by 30%, right? So you have higher lifetime. But you can also look into this plot in other way and say that having the same like by having, if I want to have the same number of the lifetime, I can actually have less powerful ECC. Like BCH code can be simpler. So it's actually the both sides. So you can have, with this similar capability of ECC, you can have a longer lifetime, or you should be able to also reduce the complexity of ECC while you have more intelligent technique to handle. And with that, I think I will stop. But yeah, there are a lot in the backup slides and also a lot of links. So if you're interested, you can check. We can also discuss later if you're interested. So thank you so much, and see you next week for the last lecture, I guess.